Our next task is based on a natural gas compressor that I found on the internet on a vendor website. Here is a picture of it. It compresses natural gas. The inlet temperature should be 20 degrees and the discharge temperature after the water cooling should be less than or equal to 50 degrees Celsius. The inlet pressure can be between 0.05 and 0.3 megapascal, and the final discharge pressure will be about 25 megapascal. The discharge capacity is about 510 to 1420 normal cubic meters per hour. The shaft power is 241 kilowatts. And the cooling method is water cooling for the gas stream. Okay, so this is our task 4. Use this data to calculate the compressor adiabatic efficiency and the required water flow rate for an inlet temperature of this water stream equal to 25 degrees Celsius and an outlet temperature of 60 degrees Celsius. Okay, now you can notice that the flow rate for this compressor is specified as normal cubic meters per hour, and let me clarify this for you. Okay, so this is a note about inputting standard condition volumetric flow rates in DWSIM. You should know that standard condition volumetric flow rates, which are commonly used in the natural gas industry, can be taken as mass flow rates and should not be entered in the volumetric flow rate input box, which is this one. You can see that you can input the flow rate of the stream in mass flow or molar flow or a volumetric flow. If you input one of them, the DWSIM will calculate the other two. You can input any one of them. Okay, so you shouldn't input this flow rate in the volumetric flow rate input box because the standard condition volumetric flow rates don't change with temperature and pressure, and the actual volumetric flow rates vary with temperature and pressure, which is this volumetric flow rate in here. If you change the temperature using this example from our task 3, you see that the volumetric flow will change. See? This is because the mass flow is kept constant and the volumetric flow changes as soon as we change the temperature and pressure of the stream. Okay? So you should not enter that volumetric flow rate in here because it is a standard condition volumetric flow rate. DWSIM automatically converts standard state volumetric flow rates if you input them in the molar flow rate text box. So if you have a normal condition cubic meter, it is the same as saying that it is a cubic meter at 0 degrees Celsius and 1 atm. Standard condition is at a different temperature, 60 Fahrenheit. And the Brazilian standard condition is a cubic meter at 20 degrees Celsius and 1 atm. And the molar volume of the ideal gas at this condition is, so for each each standard condition we have a standard volume for 1 mole of an ideal gas. So for instance, if we input that volumetric flow rate at normal condition in the molar flow rate input box, the DWSIM will convert it to mole per second as follows. So we have 510 cubic meters per hour at normal condition times 24. We have all the math in here to convert it to moles per second. Okay, so this is what the DWSIM does internally, and this is actually an approximation to the ideal gas equation of state if we consider the compressibility factor of the gas equal to 1, which is almost true because at this atmospheric pressure and low temperatures, almost all gases behave as an ideal gas. Okay, so let's go back to our problem. I've made a drawing representing our process. We have the compressor and we have the natural gas flow rate, which we will consider made of 90% of methane and 10% of ethane. It is entering the compressor at these conditions, leaving at known pressure of 25 megapascal gauge. The temperature we don't know, we will calculate it. And this natural gas compressed stream is cooled down by a water stream, which is entering some kind of heat exchanger at 25 degrees Celsius and leaving the exchanger at 60 degrees Celsius. Okay, and in the end we will have our compressed gas stream at 50 degrees Celsius. So we have the compressor power specified in the datasheet, which is less than or equal to 241 kilowatts. We will use this power to calculate the compressor efficiency. Okay, we will calculate the outlet temperature of the compressor and the cooling water flow rate. So let's build this simulation in the cross-platform user interface of the DWSIM. Let me click on the shortcut, click on new simulation. This is the setup wizard of the new user interface. Click next. It takes a while in Windows to load the list of compounds. We need to be patient here. Okay, so now let's search for methane. Press enter. Select. Click outside the checkbox to make sure that it is checked. Okay. Methane. Okay. Next. Here we can use these little boxes to quickly configure our thermodynamic model. So I know that my process deals with hydrocarbons only, so I'll check this box. Expected phases. I'm not expecting to deal with two liquid phases in this simulation, so I'll leave this unchecked. Click next. Simulation name, task 4, natural gas compression. The system of units, I'll choose CG. I'll leave it SI and I'll create a new one after we finish it. You can see that the interface now looks like the classic user interface, but we will see that some things are a little different from the classic one. Okay, so first I'll try to create a new system of units. I'll go to flowsheet settings. Okay, and here at system of units, I'll click on the create new system of units. This is my new unit set. I'll choose Celsius, pressure, I'll choose megapascal, mass flow, molar flow. I'll choose the cubic meter per day at normal condition, as I've explained earlier. Volumetric flow, this is the actual volumetric flow. I'll leave it at cubic meter per hour. You'll notice that we don't have cubic meter per hour at normal condition, so we will need to do a little conversion here to input the value at these units. Okay. Okay, so let me close it, and my new unit set is automatically selected. So let's drag a material stream. For the inlet of the compression, another one for the outlet, another one for the outlet of the heat exchanger, one for the inlet cooling water, and the outlet cooling water. And then energy stream for the compressor, the compressor itself, which is here, adiabatic compressor, and heat exchanger model. Okay, so for the connections, here things are a little bit different. I've selected the compression, and in the connections tab I'll choose material stream 0 for the inlet, outlet 1, energy stream ES5, and for the heat exchanger, the natural gas inlet, the outlet, no, the inlet stream 2 is the cooling water, stream material stream 0 2, outlet stream 1, material stream 2, and 4. Okay, so we have our, if you want to rename the object, you can go to appearance and type new name for the object here, compressor. Water cooler. For our inlet stream, I'll notice that my selection, my model selection, my selection, notice that when I selected the hydrocarbon options in the simulation setup wizard, it automatically chooses the Penrobson equation of states to model the properties in my simulation, so it is selected by default here. Let's change the mixture composition as specified in the problem, accept, update. When we click on this button, the flow sheet calculator is automatically activated, and you see that we had an error here because we didn't set up everything yet. And in the cross-platform user interface, we don't have an option to deactivate the solver. Okay, so we actually have an option here in setup, global settings, user interface. We have an option to disable the call to the solver on each editor property update. I will disable it for now, so we can change the properties of the object more easily. Okay, well, I need to set the temperature of -25. Okay, pressure, I'll enter 0.3 gauge plus 1.3. No, 0.4. Yes, 0.3 plus atmospheric pressure, 0.4. The molar flow is hour times 24. Okay. The compressor connections, properties. We will specify the outlet pressure, which will be 25.1 megapascal. You can see that in the cross-platform UI we can specify any property we want, but DWSIM will obey the selection here for the calculation mode, and we use the value that we entered in the corresponding text box, and we calculate the other ones. So even if you change it here to anything, it will be calculated when the flowsheet calculator calculates this object. Okay, so it doesn't have any effect to change the other parameters here. For the cooling water, oh, I forgot to add water to the simulation. I'll go to setup, compounds, even if I said before that I was going to deal with hydrocarbons only, I'll stick to the Penrobson equation of state just for the sake of simplicity. Okay, but the correct thing to do would be to use the steam tables property package only for the water part of the simulation, but let it be this way. Let me close these editors so we can see the water text box in this editor. So no methane, no ethane, only water. Set. Temperature 5 degrees. Pressure, atmospheric pressure. Okay. The flow rate is the one that we will try to calculate. For now, we don't know it yet. It will depend on the outlet temperature of this stream. So let's configure our water cooler here. We will select the calculation mode for this heat exchanger. We will make it calculate the cold fluid outlet temperature, which is the water outlet temperature. We will leave the pressure drop at 0 just for the sake of simplicity, and let's specify the outlet temperature of our hot fluid, which is the gas, natural gas, 50 degrees Celsius. We can leave everything else in the default values. So let me save the simulation. Task 4. Gas and cold. Okay. So now let's run our simulation by clicking on the play button, which is the sole flow sheet. Okay, so it was calculated. You will see that we already have a value for the outlet temperature. You can see it in the results tab for the material stream. Here it is, stream temperature, and the outlet stream was not calculated. Strange. Let me see what I did wrong here. Calculate cold outlet temperature. So I need to put the hot fluid outlet temperature. I think that it should be specify cold fluid outlet. Calculate the hot. Yeah, I need to fix this, but let's continue for. Yeah. Now we have it. So the outlet temperature of the natural gas stream is correct, 50 degrees Celsius. Don't worry about this bug at the heat exchanger, I'll fix it later, but let's continue with our simulation. So you can see that the water is leaving at incredibly high temperature, which means that our flow rate is very low. Let's increase it for 100 kilograms per second and rerun our simulation. We got a better result this time. Let me add a property table to the flow sheet. I went to Objects, Add New Property Table. Okay, so double click on it, and now select MS3 mass flow, show, form, temperature, show. natural gas compression efficiency, show, power required, show. Okay. So our stream should live at 60 degrees Celsius. Let's lower this. I'll re-enable the automatic calculation setting, global settings solver, user interface, sorry, call solver on editor property update. Let me decrease the size of the fonts a little bit. Click 9, 5, maybe no, it's more than 70. Almost there. 8. Okay. I think I've entered the volumetric flow at the wrong text box. And we need to adjust the water flow rate. It shouldn't be that high. 1, 2, okay. So what about the efficiency of our compression? We need to adjust it so the power required by the compressor should be close to the specified one, which is about 241 kilowatts. Let's try emission heat 197, 219, almost there, 35, oops, too much, 40, 42, no, 41. Okay, we got it. So let's adjust the water flow rate again. Let's increase it to 2, not that much, 1.7, 1.6 maybe. Okay, so here we got our results. The outlet temperature of the compressor, the power required is close to the specified one. Our efficiency calculated efficiency is 41%, and the water flow rate is about 1.6 kilograms per second, or 5.39 cubic meters per hour. Okay, so everything else is okay. And if you want to see the results of the whole simulation, you can click on the results tab, and you can select the object, and you see a text report for each object. Okay, the heat flow of the energy stream connected to the compressor. Here we have the compressor properties, the calculated properties, and the heat exchanger properties too. There are some interesting results here as the thermal efficiency, but we will see that in a later course in DWSIM. Okay, you can export this selected report to a PDF file, or export all reports to a PDF file, all to a open document spreadsheet, or everything to an open document text file, as I did with the classic user interface. Okay, so let me close.